In this video, I'm going over 10 exercises that are related to chapter 15. As you go through the video, for each exercise, you can pause the video, do the exercise on your own, and then watch my explanation and my answer. First question, which reagent is not suitable for conversion of an alcohol into the corresponding alkyl chloride? And actually, first reagent, right away, if you know what it does, tosyl chloride, it converts alcohol into tosylate, not to chloride. Tosylate is a leaving group, but it's not chloride. So that's correct answer. Just to double check, you go through the rest. Hydrogen chloride, yes, that one converts alcohol into alkyl chloride. Thionyl chloride, also suitable reagent, even better. And last one, phosphorus trichloride. Yes, that's another reagent to convert alcohol into alkyl chloride. So correct answer is A. Question number 2. Which compound is the major or the predominant product of the elimination reaction shown below? So we have alcohol, 2-methyl-3-butanol, and reaction with sulfuric acid, concentrated sulfuric acid. So the reaction mechanism involves protonation of the hydroxyl group and then loss of water to give carbocation shown here. That's secondary carbocation. It undergoes rearrangement into tertiary. So 1,2 hydride shift causes rearrangement or results in rearrangement of carbocation into more stable tertiary carbocation. And then loss of proton. Base removes a proton. Base could be water or bisulfite anion. So base removes proton, or actually even another alkene could be a base and gets protons in the process. So base removes a proton to give the most stable, the most substitute alkene. Typical outcome of E1 elimination. That would be Zaitsev regioselectivity. And the most stable, the most substitute alkene is 2-methyl-2-pentene. When we consider possible answers, B is 2-methyl-2-pentene. So a question like this you should answer on your own without looking at 4 possible answers, and once you arrive at the answer, match it with one of 4 possible choices. Next question, elimination of 3,3-dimethyl-2-butanol. By which of the following reagents proceeds without a rearrangement? In this case, you could actually write the equation and everything, but actually you don't need to do that. You need to know that E2 elimination proceeds without rearrangement. So really, this question is which of the following reagents will cause elimination by E2 reaction mechanism and not by E1, because E1 elimination proceeds with rearrangement. So first, A, sulfuric acid. That one protonates, as we have just seen in the previous question, protonates hydroxyl group leaves as molecule of water to leave resulting carbocation. That's E1 reaction mechanism. That's not correct answer. B, tosyl chloride. Tosyl chloride converts hydroxyl group into tosylate, which is a good leaving group, and then that's followed by treatment with potassium hydroxide, strong base. Those are E2 elimination conditions. So B appears to be correct answer. To double check, we should consider answers C and D. So C, phosphoric acid, just like sulfuric acid, protonates hydroxyl group, and that's E1 reaction mechanism. And also paratoluene sulfonic acid. It has the same properties essentially as sulfuric acid. It's about as strong. It protonates organic species. The only difference is it's solid and it's soluble in organic solvents. So sometimes we use that one instead of sulfuric acid. But again, that reagent favors E1 reaction mechanism. So correct answer is B. Next question, what is the product of the following sequence of reactions? So we have alcohol, and then first step reaction with tosyl chloride in pyridine. That first step will convert alcohol into tosylate, good leaving group. And then in the second, we have this good nucleophile. Sulfur, particularly negatively charged sulfur, is really good nucleophile. And so this group is going to replace tosylate group, CH3S group is going to replace leaving tosylate, and that's going to happen with inversion of configuration. So the resulting product is going to be a thioether, and it's going to be thioether B, because thioether B has configuration that is inverted compared to starting tosylate. And note that formation of tosylate occurs with retention of configuration. There is the same relative configuration because reaction occurs on oxygen and not on the chirality center, not on the carbon. Second reaction occurs at the chirality center, and that's why it occurs with inversion of configuration. Question number 5. Predict the organic product of the following reaction. And so here you have an alkene and an alcohol. So two functional groups. Reaction is with PCC in dichloromethane. So in this case, you need to know the reagent. And if you know the reagent and what it does, then this question is relatively easy. PCC stands for pyridinium chlorochromate. And that's the reagent that is used to oxidize alcohols to corresponding aldehydes, and double bonds are unaffected. And so when we consider 4 possible choices, A is the compound where alcohol has been oxidized to aldehyde and double bond is unaffected. So that's correct answer. Question number 6. Which of the following is an oxidation reaction? And we can see that we have 4 reactions and all 4 are addition across a double bond. So both carbons of the double bond may undergo change in oxidation state in the course of reaction. In this case, reaction is defined as either oxidation or reduction reaction if both carbons are either oxidized or reduced. If both carbons are reduced, that means oxidation state, oxidation number has it has become smaller in relative terms, then oxidation number has decreased, then that's reduction. If oxidation number has increased, that's oxidation. If one carbon has been oxidized, one reduced, then a reaction cannot be classified as oxidation or reduction. You may need to do calculation in each case if you cannot tell right away. In this case, there is no time to do calculation, it's trivial anyway. But in case A, you can see that we have addition of water across double bond. So one carbon has hydrogen added to it, one carbon of double bond, the other one hydroxyl group, oxygen bonded to it. So carbon with new hydrogen bonded to it has been reduced, while carbon with oxygen, new oxygen bonded to it, has been oxidized. So one carbon has been reduced, the other oxidized. This reaction is neither oxidation nor reduction. B, both carbons of the double bond have new hydrogens attached to them. That means both carbons have been reduced. So reaction B is a reduction reaction. Reaction C, both carbons have oxygens bonded to them, new oxygens bonded to them. That means both carbons have been oxidized. And so that's correct answer. C is an oxidation reaction because both carbons have been oxidized. And D, one carbon has new hydrogen attached to it, another one new bromine attached to it. So hydrogen, that would be reduction. Carbon that has bromine attached to it, that one has been oxidized. So one carbon has been reduced, one oxidized. So this is neither oxidation nor reduction. Correct answer is C. Question number 7. In the compound shown below, charges, if any, are not shown. So oxygen atom has, so what is its formal charge and oxidation state? The best thing to do is to do calculation on your own and then match that with one of the possible answers. So for formal charge, we start with number of valence electrons in ground state. For oxygen, that's 6, minus number of assigned electrons. So 2 electrons from free electron pair are assigned to oxygen, and there are 3 bonds on oxygen. From each bond, because those are covalent bonds, we assign half electrons to the oxygen. So 3 bonds, each has 2 electrons, so half of that would be 3. So 3 electrons from bonds are assigned to oxygen, plus 2 from free electron pair, that's 5, 6 minus 5 plus 1. So formal charge on oxygen is plus 1. Oxidation state, we again start with 6 electrons in the ground state. 6 valence electrons in ground state minus number of assigned electrons. But now electrons from bonds are assigned to more electronegative atom. Oxygen is more electronegative than carbon, so all of the electrons that oxygen is sharing to carbon are assigned to oxygen. And oxygen is also more electronegative than hydrogen, so that electron pair oxygen is sharing with hydrogen is also assigned to oxygen. So all of those electrons around oxygen, 3 bonds and 3 electron pair, all are assigned to oxygen. That's 8 electrons. So 6 minus 8 minus 2. So correct answer is formal charge of +1 and oxidation state of -2. And that matches answer C. Next question, what is the product of the following reaction? We have reaction of an epoxide under strongly basic conditions. Second step is workup, simply to protonate the resulting anion, oxygen anion, alkoxide. So strong nucleophile methoxide means that reaction is typical SN2 reaction and is sensitive to steric hindrance. So nucleophile will attack or form a bond to less substitute carbon of the 2 carbons that form epoxide ring. And of course the other carbon will end up upon protonation with hydroxyl group. So if we consider possible products, we can see that that matches product B. Question 9. What is the major product of the following reaction? So here we have Hofmann elimination, and on the nitrogen we actually have 2 alkyl groups that could eliminate. We have on the right isobutyl substituent and on the left 2-pentyl substituent or S-pentyl substituent. So question is which one of them is going to eliminate and what are the possible products. So when we consider possible products, isobutyl substituent as a product could give 2-methyl propene. That's disubstitute alkene. On the other hand, 2-pentyl substituent can give 2-pentene, either cis or trans isomer, or 1-pentene. 2-pentene is disubstituted, 1-pentene monosubstituted. We know that Hofmann elimination results in formation of least substitute alkene. When we consider 3 possible alkenes, the least substitute alkene is 1-pentene. And so that's going to be the major product of this reaction. Next question, what are the products of the reaction of methyl isopropyl ether with hydrogen bromide? Hydrogen bromide will protonate oxygen in the first step, and then because one of the substituents of it on oxygen is secondary, the alcohol will leave as a leaving group to leave secondary carbocation. Secondary carbocation is going to combine with bromide anion to give the final product. So secondary carbocation reaction with bromine with bromide anion gives 2-bromopropane. That's going to be one product, and leaving group was methanol, so the other product is methanol.